Hello. Hi there. Welcome to this MATLAB live stream. My name is Jose. Thanks for being here, and I'm here with Mihir today. Mihir, would you like to introduce yourself?
Sure. Hi, everyone. My name is Mihir Acharya, and I work in the autonomous systems and robotics team with Jose, and my role is to manage the products such as navigation toolbox and UAV toolbox that specifies applications for autonomous navigation. And really excited to be here and welcoming you all to go over this topic on applied AI for robotics today.
Yeah, thanks, Mihir. And I also work here at MathWorks. I'm part of the robotics systems. And today we have a really cool live stream for you. We're going to be talking about artificial intelligence and robotics. So we have a sort of pretty packed agenda. We're going to be covering a couple of different demonstrations and applications for robotics. So in here you can see a couple of the things that we'll show you today. There is something using large language models such as ChatGPT to control robots, some perception work for manipulation, and then we also have some things for mobile robots and some reinforcement learning as well. We hope you like it. This is the agenda. First, we'll start with an introduction to artificial intelligence within robotics and the landscape of that, and why we should even consider it when we're working on developing robots. Then we'll touch on the three base demos and applications: perception and sensing, planning and decision making, and control system design. And at the end, we'll wrap it all up and summarize what we covered.
All right, so we would like to start with a question for all of you, just to get to know a little bit more about how you're joining today and where you are with your experience in robotics. So there should be a poll popping up on your screen, and we would really like to know if you are new to robotics and here to learn, if you're already studying robotics, or you're a working professional, or already working on research projects for robotics as a robotics researcher. So yeah, please go ahead and select one of those options.
And we'll take a look at your results here in a second. If you can just go ahead and add some of your answers there. But this session should cover good material for all of these different stages of your career as well.
Absolutely. Yeah, so we have resources at the end for those who are new to robotics or studying robotics already, and for someone who's building robots or programming robots, you'd find several different built-in applications that we will show today that you can directly adopt for your robotics applications.
Okay, let's see if we have any results from the poll. Otherwise, we'll go ahead and continue for a bit.
Yeah, we can take a look later.
The first thing we're going to cover today here is large language models. Those are pretty popular.
Awesome, yeah.
They've been popping up everywhere. You've seen them, ChatGPT, Google Bard, and how can we use those for robotics? So,
awesome.
The first thing we wanted to show everyone is this demo that we've been working on here at MathWorks. It's a low-cost robot, so it's a small 3D printed robot that can point at things and move things around. It's pretty cheap. It's controlled by an Arduino, a microcontroller. And we developed this UI, or this user interface, where you can write prompts and ask him questions. In this case, this is sort of a Formula One related demo. So you can ask him questions about racetracks and their locations. So in this case, we asked it what country has a track that's very close to the desert. And then the user interface gives us the answer, which is UAE, United Arab Emirates. And then the robot itself can then receive that information, it processes, and then it knows where it should point to in a map. So that's a world map there that you see on screen, and then you see the robot pointing to, United Arab Emirates country in the map.
Awesome. So if I get it correctly, so here we are highlighting the human-robot interaction part, and the AI part is really towards more on how we are giving the commands and how we are asking the question, and the large language model, ChatGPT, is able to process that and convert it into something that the robot can understand.
Yeah, exactly. So basically we're reusing sort of a ChatGPT API. It's just a way to plug into the existing intelligence that somebody else developed. And then all we're doing is creating that connection in between the sort of intelligence from the large language model to the mechanics of the robot. So we do that through MATLAB, through interfacing a library with the robot, in this case an Arduino. Yeah.
Awesome. Can you also briefly let us know how we are doing this in MATLAB? Do we have some sort of interface in MATLAB to connect with ChatGPT?
Yeah, so for instance, we'll put a link in the chat. There's something called MatGPT, which is sort of a file exchange submission. It's an available sort of third-party library that you can use to connect to ChatGPT API and send prompts and receive information.
Awesome.
Yeah. And here's just another prompt that we had for it. So you can ask it several questions. It will point to different racetracks in this case. So that's all with regards to how you decide to integrate that information into your algorithm. So we ask them like which country has a track that's situated on public roads, and then we get an answer, in this case Australia, and then the robot will again process that information and then point to a different place on the map, in this case Australia.
Awesome.
Yeah. All right, so just moving along with the artificial intelligence concept, it's obviously present in our everyday lives, things like Alexa, Siri. It's integrated in our phones, in our houses, in social media, and even in our cars. So it's natural that it will trickle down that technology into robotics.
Yep.
Now, robotics is sort of a big field. There's industrial robotics, there's robotics for research, there's robotics for interactions with humans. But mostly we can bucket the use of AI in robotics into mostly three categories, or these are the categories in robotics where it can be applied to. There's traditional robotics where it's mostly just hard-coded tasks, kind of pick and place, where there's no human assistant. And there's Cobots, or collaborative robots, where there's a robot and a human in the loop. Yep. And you want to account for some safety and some interaction, and then there is some instances in which AI will be useful in there. And there's completely autonomous robots, which is sort of the third category there, fully autonomous or highly autonomous robots. Those are the ones that benefit the most from using artificial intelligence.
And AI is something, I guess, that can be applied to these autonomous robots, but there are also traditional autonomy algorithms that were used prior to these deep learning networks came for robotics as well.
Yeah, absolutely. That's a great point, actually. And if you're interested in sort of the more traditional methods of programming and developing robots, we have a couple more live streams and videos that you can check out. On this one in particular, we'll focus on the sort of AI, artificial intelligence portion. And just to give you an idea of how this works, normally you'd program a robot with some data, and you'd have a programmer that has some human insight create a program for a task, and then you program the robot will generate that task, will operate within that task and create an output. However, when we're dealing with artificial intelligence or trying to integrate it into robotics, what we're going to do is we're going to start with the task. We're going to start by showing the robot how to do that task, or showing the mechanism how to do that task, and gathering a lot of data, and then using that, putting it into a training algorithm and getting the program or the set of instructions out of that. And that's what we call in sort of deep learning a model. That's a deep learning model that will be used within the robot later on. And that is all part of artificial intelligence, which is then sub-bucketed or classified as either deep learning, reinforcement learning, and those are both also categorized as machine learning.
So I really like that switch between program and output. So in artificial intelligence or learning methods, we are really showing the output to the robot first and training it based on that output. And then when it gets to see the similar task, then it's able to predict or work on that based on prior training.
Yeah, exactly. And sometimes that's a lot of output, which means a lot of data, which is normally the case when you're trying to train something. One thing to keep in mind is that we call these deep learning models also sometimes black boxes, because contrary to a programmer writing down a set of instructions that are clearly identifiable and understandable by another human, these black box models are created by a computer and are not easily understood by a human. They're a set of parameters and equations and math. Yeah. So And then onto what we're covering today. When you're developing an autonomous robotic system, there's generally three main pieces of development that you focus on, which is sensing and perceiving the environment, planning and deciding, which is sort of the intelligence part of the robotic system, and then controls or control system, which is getting to the mechanics of the robot interacting with the environment, the actuators, and how to control those. Of course, there are various ways in which you can apply artificial intelligence to each of this. We're going to show you one example for each of this. For sensing and perceiving, for instance, you can do computer vision, you can do image processing, traditional methods, or you can use artificial intelligence. The same goes for if you're trying to do something like SLAM or localization or sensor fusion and tracking. And we'll cover the three of this, but for now, we'll focus on sensing and perceiving. And for sensing and perceiving in particular, we'll see that it's fairly adopted in industrial robotics and just commercial robotics already. For instance, for voice commands, so you can do voice recognition and then identify it, just like we showed with the other demo. You can do object identification for robotics, or you can do more of the inspection, so identifying faults within objects. And what we want to show you here is that these are all like already developed applications that different customers of ours or different companies use already. For instance, Yaskawa, which is a robot manufacturer, and some other research labs. These are some applications that are already being adopted.
Awesome.
Okay. So that being said, we're going to be talking a lot about deep learning networks today, especially on the sensing and perceiving portion for image classification. So that brings us to our first demonstration, or our first case study, which is a pick-and-place robot. So I'll go ahead and place this video. So in the video, you can see that we have a robotic arm, and particularly this is a Canova arm, and it's picking up what's called PVC fittings. And the way it's doing it, it's identifying those fittings, and then it's determining how to pick them up. And it's a non-trivial task because, contrary to a human hand, the robot only has 2 fingers, and if it doesn't line up those 2 fingers correctly, then it's going to drop that PVC fitting. So this is what we're going to show you. We're going to show you how we were able to make this robot complete this task, and it involves, again, artificial intelligence in the form of deep learning, and identifying those PVC fittings and identifying the correct, what's called grasping orientation. The first thing you need to be able to train, sort of a deep learning model, is a lot of data. And one of the ways of doing it is by using a simulation. Of course, you can also do it with the real system. So these are just options. So you'll see here, in our case, we did a combination of both. So we used a simulated system, in this case in one of our products, to generate random locations for all of these PVC fittings and take a lot of different pictures. And then we also used a real setup and then moved the PVC fittings around and took a lot of different pictures from different angles.
So I think the importance of data preparation really comes down to how big of your data set is and how many different angles and shadows or different lighting conditions you train the robot perception sensors with. It gets better and better with detecting in new situations. Exactly.
That's a great way to wrap it up. The more data you have, the more accurate or the better you can train your model, but it also means it might take longer, and obviously you're going to have to label and work with that more data, which takes more time. So there's a balance there. And then you can also generate data with other tools. For instance, this is just showing you that this is ISAC Sim, NVIDIA ISAC Sim. It's another simulator. You can also use other simulators to generate what's called synthetic data. In this case, it's artificially generated data. Okay. We'll go ahead and jump into MATLAB real quick. We'll show you a little bit of the scripts that make this possible, especially on the intelligence side, on the deep learning side. Again, what we're trying to do here is identify those PVC parts and then segment them, identify them, isolate them, and then determine how to pick them up. The way we do that is by training a YOLO v4 network. In this case, this is a particular type of network that you can perform transfer learning on. And we're going to do that. We're going to retrain that network, do transfer learning, with new data. Basically, we're going to label our own images, and then we're going to run a training function on it, and then we're going to get another network that's going to identify the objects we want.
And do we have this YOLO v4 built in comes out with MATLAB?
Yeah, actually you can install it. It's part of the add-ons. So if you go to Deep Learning Toolbox, you'll see that there's many different sort of off-the-shelf type of neural network architectures, and you can just install them in your MATLAB, and then they'll be there available for you.
Awesome.
So we'll try to be really quick through this, but what we want to showcase here is that you're going to have to prepare a lot of data. In this case, we're importing a lot of data into something called an image data store, and then we're going to label it. So what we want to show you here is how the labeled data looks like. So this is an image that we gathered from one of our simulated environments, and the idea here is that you're going to have hundreds or thousands of these images, and you're going to have to label them with all these boxes. In this case, we're identifying the fittings as by letters like X, T, I, or L. And we go ahead and we draw these boxes, these bounding boxes, in each of the elements. And then technically we have to do this for hundreds of images. And that's where MATLAB is really useful, or any software tool that has a labeling tool. So we'll cover it a little bit later, but we can speed up that process of labeling by using some other algorithms to automatically label as well. And then once we have all that labeled data, we create a detector, in this case a YOLO type detector, with some sort of function. So you can see here, in this case, this is the function that we'll use to sort of import a detector for the YOLO architecture. And then I'll skip through some of this code, show you this is just an example of many labeled images. And then we'll get to the training portion, for which we'll have to set some options. If you're not familiar with sort of neural network and deep learning training yet, we have plenty of resources and some tutorials. You can check out what the specifics of the training options mean. But for now, we'll just showcase that you can use this function right here, in the case of the YOLO type detector, to train it. It says train YOLO v4 object detector, and you'll pass in your training data, the data that you've labeled, your detector, and then those options, and then you'll essentially let it process that, and it'll take a couple of hours for it to train. And at the end, what you will get is some metrics. For instance, these are some of the graphs that you get from the training process. The total loss. The loss just means basically how many mistakes your neural network is making on classification. And if that graph's going down, then that's good. That means that you're training in the right direction. And then something like the learning rate, which just slows down towards the end. In this script, we also have some metrics. So you have something that's called the recall. So you can see that it's close to 1. So the average precision of this neural network is 0.89. So if that's close to 1, it means that it's essentially pretty smart at identifying the objects. It does a good job. And finally, to sort of complete the whole workflow after we've identified those fittings, we go through a couple of extra steps, which include a little bit of sort of CAD and a point cloud processing, which is sort of a 3D sort of a mesh. And these files are available online. You can look at them after, but we'll just give you a conceptual explanation. So we have available the rough shape of the object from CAD. And what we do is we try to match that rough shape to the one that the camera is seeing. And the camera has a point cloud representation, or it has depth information. So what we do is we'll skip through a couple of these, as we've identified some specific positions in which these are easily graspable by the robot. And after we've identified each fitting through that neural network, we try to sort of orient the shape that we have to see which is the best position to grasp. and we assign this sort of red orientation marker. And then the robot uses that to sort of go to that position and orientation and pick it up. Here's the neural network identifying the objects. So we can see that it's labeling them correctly as an L, X, T type of object or type of fitting.
And I think it is also showing the accuracy and confidence of how, with those numbers there, right?
Yeah, exactly. So if you look at these numbers right here, they're all pretty much 0.99, which is as close as you'll get to 1, which means that it's actually pretty smart in identifying the object.
Mm-hmm.
So we did a good job in preparing the data.
Yep.
And then we do a couple of other computer vision sort of tricks and algorithms. So we segment some of the image, and then we try to match that point cloud data to the shapes that we have. And we end up with this, which is sort of the orientations. You can see the coordinate frames in there that tells us what is the appropriate orientation to grasp each of the fittings. And then we just loop through all of the fittings that are available in the table and pick them up one by one. Okay, I think that wraps up this first demo. So we'll go back to the slides real quick. And
so when you're doing that, I just got the results of our first poll, and it's interesting that we have a good mix, around 43% students, 21% working professional, 4% robotics researchers, and 30% new people. So we've got a lot of people interested in AI.
That's awesome. Yeah, we have some researchers, we have a lot of students and some professionals. Great spread. Thanks for attending. Yeah. And if you have any questions, you can start putting those in the chat. We're going to take a couple of breaks to answer those questions as well.
Awesome.
Okay, so we covered how to generate synthetic data. There's more options. Of course, we only covered generating like images for this particular demo, but you can also do it to generate, images for semantic segmentation, LiDAR data, or other types of applications. You can also train your object detectors in MATLAB, which is what we covered today. You can automate the labeling process, which we mentioned. Here's just a brief video of how the automatic labeling works. Essentially, you can label, let's say, 5 or 10 images, and then create a sort of low-effort detector that will try to label hundreds of them for you. And then you can go back and fix anything that's incorrect manually.
And I think that takes out a lot of tedious tasks, right? Labeling the data, if that's automated, saves a lot of time.
Yeah, so I think, as we mentioned, the data is the most important part, so that really helps. You can correct the labels. So we'll skip through some of that. As we mentioned, we talked about YOLO today, but you can use any other sort of object detection architectures. You can use things like Solo for segmentation, or other more robotic-specific or different type of networks that I've developed, like this hand pose estimation. And if you're interested in mostly working with the sort of deep learning, sort of image classification side of the algorithm development, we have lots of tools like the Deep Network Designer, which is a graphical tool to evaluate your network, a classification learner app, which again is just a set of tools to help you navigate those experiments, and an experiment manager which helps you run lots of training options and experiments so that you can sort of leave it running over time and then come and evaluate your results. One thing that's important to note is that you can get all of these neural networks outside of MATLAB. So if you develop them in MATLAB, you can use them in other tools like PyTorch. And if you're developing the network in other tools, you can also import those into MATLAB to work on your robotics development, right?
Yeah, that interoperability gives a lot of flexibility with choosing. If you have any other network developed in another platform, you can bring it in MATLAB and test it or compare it with the other workflows you have developed in MATLAB.
Yeah, absolutely. You don't have to worry about whether you can integrate that into your algorithm.
Awesome. So we are up to our next poll. So here we wanted to learn more about, of course, this is something applicable to those who are working on some robotics applications or planning to work on some robotics applications. So we really wanted to know what type of robots would you like to apply AI to. And the options we have here are mobile robots, which are kind of robots that are running on the ground, like delivery robots, or those robots that are running in factories from point A to point B. Then we have robot arms, as Jose earlier mentioned, collaboratively working with humans or in industrials, or UAVs or drones, or even in future we are looking at flying taxis. So if that is something you'd like to see AI with, or with self-driving cars, so cars driving autonomously on the roads. So where is that you'll like to see AI applied to, or if you see value of AI the most?
And while we're waiting for that, if you have any questions, we can take a couple of questions. If you want to put them in the chat, we'll get them here in the studio and we can try to answer those as well. If you have any questions related to anything we've covered so far, the first demo, things like that. Are there any questions? Okay, so we have a question. Do you make labels for real and synthetic data, or just real data? So Mihir, do you want to give that a shot, or?
I think it's possible for both, right? It depends on what data you're providing to the app. And
I think, yeah, both of them are fine. So you can label the synthetic data, or you can label real data. Depending on the simulator and the images that you're getting out of your synthetic data, those will translate well to, let's say, your real-world application. It might not, but generally it's a good start. So generally, if you only have access to synthetic data, it will be a good start to label and train on that before you get access to more data to verify with. Yeah. Any other questions? Okay, so with that, I'll pass it over to Mihir. He's going to walk you through the next set of 2 demos. And we're going to be
Awesome.
talking about planning and deciding. Yeah.
Sure, I can share my screen from here. And we'll just switch over in a moment. All right, so we saw how we can perceive the data and get information from the environment. But once we have the knowledge of the environment, the next step for the robot is to plan and decide the actions. So that's what we are going to talk about in this section, and how we apply AI and deep learning based algorithms for that. So for planning and decision making, motion planning is one of the techniques that we use from moving the robot from point A to point B. And quickly giving an example, look at this warehouse floor plan, or similar to a parking lot as well. If we know the map of this environment using our perception algorithms, we usually get an occupancy map that classifies the map into free space, or occupied space, or obstacle space. In this case, all the black lines are obstacles for the robot, and we want the robot not to collide with it. So the goal here is to move from initial location to the goal location, and we want the shortest path that the robot can take to reach the goal location. And we do that by using some path planning techniques, where the robot segregates or discretizes this map into a grid, or we can use a sampling-based approach where it samples multiple nodes to kind of then create a tree and move through that tree to the goal location. So there are several different algorithms, and we'll look at some of those. So this is something called global planning, when we move from point A to point B on a big map. But while we are moving through this or following this path, we could also encounter unknown obstacles on the way, like a pedestrian or something that initially was not recognized in the map. So in that case, the robot really has to do local replanning to avoid that obstacle, and then merge back with its global plan to be able to reach the goal location. So this really makes it safe in different situations where there are multiple dynamic obstacles, like a parking lot.
And in this example, it looks like maybe like a car was pulling out, and then it had to adjust for that, right?
Yeah, yeah.
Okay.
So This specific example is using an algorithm called hybrid A star, which is a traditional motion planning algorithm for search-based or grid-based maps. And however, what we are going to focus on is sampling-based planning, and the reason for that, I'll go over that in a bit. So sampling-based planning has multiple different algorithms, and rapidly exploring random tree, which is RRT, is one of the most popular motion planning algorithm. And there are various variants of that, like RRT star or bidirectional RRT. But what RRT or sampling-based planning is we'll quickly go over that before we jump into the deep learning part. So it is something where we randomly sample a lot of nodes inside this state space. And what is a state space? It's when we make the map into a set of states, which is the x, y, and theta, the position and the orientation of the robot constitutes to make a state of the robot. And then we have multiple such states that the robot can take as valid states. And then what we do for this type of algorithm is we create an initial search tree by randomly sampling nodes. And then we randomly sample node and find the nearest node within this tree, and then we try to connect it with another randomly sampled node. And we keep on doing that until we find the goal node, and then we use a search-based algorithm like A star within this map to find the shortest path. So you can see that there are so many nodes or states generated here that were unused, and that's where deep learning come into the picture. And why we use sampling-based algorithm is because this is really good for high-dimensional search spaces and non-holonomic robots, such as robots that can drive with a car-like motion, or manipulator arms that has more than 2 degrees of freedom. So the traditional approaches for grid-based are very computationally heavy to make those kind of large maps, whereas RRT is computationally efficient in those situations. Now, I would like to quickly bring your attention to this ebook that we have, and this is something that I would really encourage you to try out. And this is a web page interactive ebook. We have an example here. If you have a MATLAB login ID, you can try out this example online, which shows you how to run a traditional RRT algorithm. And this ebook also has multiple other applications, some basics and definitions for what motion planning is, what is state space, and other definitions here. And then, as I mentioned, the search-based planning and the sampling-based planning. But what I really want to focus is about this 4-step motion planning workflow that we use in order to implement a sampling-based algorithm. So first we represent the state space, then we define a state validator, which is basically that lets you know if a state is valid or not. And then we sample several different states so we sample new states and check for validity for each. And then finally, we represent a collection of valid states as a path. So where does deep learning come into the play? So it essentially is used for sampling new states. So, and that's what we'll see in our next demo, and I'll switch over to MATLAB in a bit for that. But before I do that, let me go over quickly to my slide deck again.
Yeah, so I think just as a recap, these are sampling-based methods, which means that if you see in this image right here, they sort of sprinkle, these samples all around a specific map for a mobile robot. And the more of those sort of states or those reference points you have, the more computationally intensive it's going to be to come up with a solution, right? So.
Yep. So, as Jose said, this is the uniform sampling where you uniformly sample nodes all over the map, and then it expands the tree in all directions, and then it finds the shortest path. Once the randomly sampled node hits the goal node, we find the shortest path from start to goal. But in this, we waste a lot of computational resources and time because we are randomly exploring the tree. Right. And what we can do with deep learning based approaches, we can bias the nodes or the nodes that we were randomly sampling. Instead of that, we sample it only across the path. And that lets us save a lot of computational resources and time as well. So how do we do that? So we use something called motion planning networks for that. And I won't go much into detail on what this motion planning network is, but I would really like to go into a live demo that lets you show how to implement that. So let's switch over to MATLAB really quick here. All right, so this is an example that we ship out of the box with Navigation Toolbox that lets you train a deep learning based motion planning network for sampling based algorithms. So as you said, as you saw with previous demo where Jose showed a lot of different images to train the robot to finally then detect a specific type of object. Here we are training the robot with different paths that it can take in several different environments or maps. So that once it is given a new map, it can find a new path based on the prior knowledge of a lot of different paths that we gave it for training.
So does that mean that you have to sort of label different maps and then create that set of data before you can start training this?
Yeah, so here what we are doing is we have an image here. These are like randomly generated maze maps. And then we can use the traditional RRT algorithm to generate randomly. So we select random start and goals, and we generate paths using traditional RRT to kind of find the shortest path between them. And that becomes the training data for the motion planning network.
Nice.
So this is initially in the script, we are just providing the data set. Here we already have a data set created, but you can also bring in your own maps or generate new maze maps and create different paths in it. And then really quickly going to the next section. Here we are creating the motion planning networks. So this example is particularly in a 2D space for something like a mobile robot, but they can also be used in higher dimensional spaces. So the good news is the time complexities with these motion planning networks is constant with increase in dimensionality. So it doesn't the complexity doesn't increases exponentially if we use this for a robot manipulator, which has several more degrees of freedom. So what we do here is we are training the deep neural network, and what we want to do is minimize the loss functions, and we have some weights defined for that. And further, we prepare the data for training. So here we are splitting the data 80 and 20. So we use 80% of the data for training and 20% for validation. And then further, we train our deep learning network. So I think that this is a very important step. What we do here is we want to decrease the loss value, and you can see here we have a pre-trained network with all the deep learning parameters specified here. So for now, I would just set the training to false because we already have a pre-trained network here. But what you can do is you can set it to true when you have your own new data and you want to train the network for that new data. And it takes a couple of hours to train that. But what we can also do is we can use parallel computing to speed up that training. So here you'll see like a trained network, how the output looks like. So we have the validation loss and training loss. And what we really want is we want to minimize the validation loss. And the training loss will minimize because it is the same data that the robot was trained on. But eventually we want them to converge the training and validation loss. All right, so once we have trained our network, we store it in a state sampler MPNet object that we ship out of the box. And this is now what we have as our state sampler that we can use further in the traditional RRT as a sampler to sample nodes biased towards the path.
So in artificial intelligence terms, it would be like our deep learning model, right? Like the black box we're going to be reusing, correct?
Exactly.
Yeah.
So another thing I would like to highlight is after we have generated this sampler which can generate learned samples. By learned samples, I mean the ones that are biased towards a predicted path. We can also choose how many maximum number of learned samples we want to include. And that is something we do because we can actually mix the uniform sampling and learned sampling approach. Okay. And that is what we will do in our next example here. So here now we are essentially using that trained network for the sampler to generate a path. So this is the chart we saw earlier with uniform sampling and learned sampling. We have created our motion planning network here. And then similar to as I showed earlier, we are creating our state sampler here. This is the traditional state space sampler, the SE2 for uniform sampling, and this one is the motion planning network, and we are doing the both side by side to compare them. Then we generate random maps. So as we saw earlier, we trained using something like this,
Right.
and now we are generating new maps so that we can see how our trained network is working. Then we can pick a random start and goal here. We have some interactive sliders for that. So we picked the start and goal. And finally, we can plan the RRT star path. And this is a script that lets you do that. And we can see once we plan the path with uniform sampling, as we saw earlier, it is generating the tree all over. However, with the MPNet sampling, we can see that it is biased towards the path. Now, how do we compare these, and how do we evaluate performance of motion planning algorithms?
Right.
So we have multiple metrics, and we ship a lot of them in our planner benchmark object. So we'll quickly go over those visualization metrics here. So this one is execution time. So one of the most important thing we want to see is how quickly we can find a path, because the robot doesn't want to wait at one point stuck and thinking where I need to go. It needs the path really quickly so that it can start following it. So here we can see that MPNet really gives you lower planning time, as well as the dispersion is also very less. So we get consistent results in multiple iterations. The next is path length. So we want to take the shortest path so that that is directly proportional with the how long it takes for execution as well. So here we can see MPNet is able to generate by a lot of difference. It can generate shorter paths, and again it is more consistent over multiple iterations.
So it looks like it's just overall just a better planner, right? So
Exactly.
what would be the sort of drawback of using this approach?
That's a really good question. So a drawback is it can sometimes it cannot generate a path at all.
Okay.
Because of the sampling it does. So the best approach is to actually merge the uniform sampling and MPNet sampling, and that is something we showed.
So a combination of both, right?
A combination of both, exactly. Mm-hmm. So that actually gives us the guarantee that there will be a path, because if the learned samples are not good enough, we can generate some randomly sampled nodes, mm-hmm. and it can find a path out of that.
Interesting, yes.
All right, so that was that. Now let's switch over back to our slide deck here.
And of course, there'll be a little bit more overhead, right? Because now you have to go take yourself through the effort of, training this planning neural network. So in that sense, it's a little bit more development effort up front, but you end up with a much faster and more efficient planner.
Yep. All right, so that was how we plan a path. Now, once we have a path, we want to generate control commands for the robot to be able to follow that path. So that's the next step in the workflow. And here we use reinforcement learning, which is a very popular technique that translates really well to robot control. And what reinforcement learning is, it is basically a process of learning a behavior through trial and error interaction. So it relies on a combination of reward and penalty approach, similar to how you would teach a dog or
Sure.
So the RL agent interacts with an environment, and based on the actions of the system, the agent is either given a reward or a penalty, which helps it learn which action it needs to take in future. So after we have trained the agent, it can perform the tasks with the most desirable behavior. And now here we can see that there are multiple approaches that were derived for reinforcement learning, like lookup tables, polynomials, but what we are really focusing here is the deep neural networks, how we train them for reinforcement learning approach.
Sure.
And we use deep learning based policies here because a lot of different applications has very complex parameters like self-driving car or a walking robot, and the lookup table approach can be very tedious for that reason.
Okay, so I think it'll be good, Mihir, I think you have some information here. this diagram on the left looks like a very traditional control system
Right.
diagram. This is something that we would see in like a controls course.
Yep.
This is sort of a standard, plant controller architecture. How is it different to the reinforcement learning system?
So the good news is, to understand a reinforcement learning based system, it is not very different than traditional approach. We can map a lot of parallels between them. So the controller in a traditional controller system is something we call policy in a reinforcement learning system. Then the plant represents the environment. And the measurement in our plant is observations, signals in the reinforcement learning system. Then we have actions, rewards that are originally cost functions in our control system. And finally, we have the RL algorithm, which is the adaptation mechanism.
So basically that RL algorithm is what in a traditional control system would be the engineer adjusting the parameters,
Exactly.
right? Okay.
All right, so let's quickly go over a demo we have here to showcase this. So as I mentioned, we have an environment which is basically our robot model, and we can use something like Simscape Multibody to build a robot model where you can import CAD files and generate a robot, and also define real-world physics like contact forces within that environment. And then we define our reinforcement learning agent, and we'll talk more about that later. But what we can essentially do for these applications is we can train the robot to pick an object, and by the behavior that when it is not able to lift the object, that is, we penalize the agent, and when it is able to pick it up, we provide a reward function. But let's take a more challenging example, which is a ball balancing example. So here we have a plate attached to a robot arm, and the task is to balance the ball on this plate, which is pretty challenging. So let's quickly jump over to MATLAB and see how that happens. So we have a model, Simulink model, that can do that, but I would quickly go over to how it looks like in Simulink.
Pretty
So
cool.
yeah, it started with the ball started from the edge, and it can balance it in the center.
Yeah, so the ball almost fell off the little platform, and then it managed
Yep.
to keep it in there. Very cool.
And this is basically an example for that. And I'll quickly go over which deep learning reinforcement learning agent we are using here. So the reinforcement learning toolbox provides a lot of different agents that can be used for different examples or different applications. For this particular one, we are using soft actor critique, or SAC agent, which is a very popular reinforcement learning method. It's an off-policy actor critic deep learning network, and the aim is here to maximize expected reward. And we have one actor and two critics here. So we'll quickly go over the demo.
And this will be available too. This is a shipping example in our product, so you can go through the link and download it, try it out by yourself afterwards if you're interested.
Yep. So this is how our model looks like. We have the environment here and the agent here. So I'll quickly go over here in the environment, and this model shows where all the Simscape Multibody physical assets here. The plate is attached. We have a ball with a 6-off joint, which lets the ball freely roll over the plate. So quickly looking into our environment robot model here. So it's a series of multiple actuators and links, and we are actually using only last two actuators. Everything else is not being used here. So let's quickly look at the three signals that the environment generates: reward, observation, and done. So the observation signals are basically a bunch of position, orientation, and other physical parameters. And then based on this observation, based on the actions it takes, we generate these observations. And then we reward using this reward function, which is a mathematical function. So we see that the reward is a positive function here, and the penalty is a negative function. So for plate orientation and control, we want to minimize the control effort. We give it a penalty, but to make the ball move closer to the center of the plate, we give it a reward.
And this is where most of the development work would go in, right? Into designing this reward and observation functions, right?
Yeah. And then we will quickly go over to MATLAB to see how we define our reinforcement learning agent. So this is the script where we define rest of the example. And we already defined the environment in the Simulink. Here we are defining the network for the RL agent, and you can see it's a combination of fully connected and RLU layers. I won't go much into detail just for the sake of time here. And finally, we train the network here, and that's the most important step. So what we are doing here is once the agent is created, we are training the algorithm and again specifying all the training parameters. And again, it takes a lot of time to train, so we can set it to false and use a pre-trained network that we provide, or you can set it to true and train it using parallel computing as well to speed up the training. And here is what we see as the output for the training. And finally, as we saw already, we can see the result after running this example on how it balances the ball in the center. So I would quickly go over back to my presentation to show you some other cool applications you can use reinforcement learning for. So this is another one where we have a delivery robot. And again, it's a dynamic environment, as we saw. But you can also use reinforcement learning in these photorealistic environments to train the algorithms. But we start with a simple map like we have seen earlier, and we train within this simple map. Then we test it after training within the simple map. And finally, we translate it over to this photorealistic environment and test it over there before finally deploying it on a real robot. Similarly, we have another example where you can see a bipedal robot is being trained to walk. And again, we have several different penalties for it to kind of learn the behavior of walking, and then we give it rewards when it is able to walk properly. So finally, we can see eventually it learns how to walk with.
Yeah, it looks a little funny, but it gets there, yeah.
Yeah.
And I think one thing to mention with regards to reinforcement learning is that it may not be a replacement to your traditional control system development approach. It is very useful in certain applications, and it will be up to you to decide to whether it's the right choice for your application. But in general, highly nonlinear systems benefit from sort of letting the computer figure out some parameters, right?
All right, so with that, we are towards the end. So finally, we wanted to mention that all of these simulations, once they're validated, you can actually deploy them directly on these real-world applications. And we provide automatic code generation capabilities for these several different platforms like ARM processors or NVIDIA Jetson boards or FPGA. We also connect with ROS robots. We have a product called ROS Toolbox that lets you generate ROS nodes that you can directly run as executables on these ROS-based robots. And here is one example from the initial demo that Jose showed, where you can actually implement that in simulation as well as on the real robot. Here we have the Kinova robot finally running the whole setup.
Right. So if you're wondering how do you go from developing this in MATLAB to putting it in an actual robot, this is basically how you generate some code and you compile it in the platform that you're going to have running continuously.
And that's the beauty of having everything in one environment. You can simulate there, you can scale your applications for larger data sets, and then you can deploy from there itself without having to rewrite or hand code again from scratch. All right, so we covered a lot. And Jose, would you like to summarize what we had today?
Yep, so we'll summarize what we covered today. We're going to have some time for some questions. If you want to put some questions in the chat, we'll cover them in like 2 minutes. So we covered why use AI for robotics. Again, 3 different applications. How to help robots sense their environment. Things like natural language processing, machine vision, object detection. How to help them think or how to act. That was planning and decision making, so reasoning or planning. In this case, routes through environments is what we showed you today. And then how to help robots act. This was the control system portion of the talk, which was more of how to develop control systems for robots, in this case using reinforcement learning. And there are several applications that you can apply this to so that you can add artificial intelligence to your robots. Awesome. And just a recap on how you can use MATLAB and Simulink for all of this workflow, again, with ranges from data preparation to developing the models themselves, editing those, validating those, using simulations to either test those models or generate data to train those models. And then finally, you can do deployment, so you can generate code, get your algorithms outside of MATLAB, put them in your application, and have that implementation ready.
And I would like to add that this is really helpful for those who are already working on robotics application, but AI is new to them. They can really use these built-in models for AI and apply on their robotics applications.
Okay, and we have one last poll for you before we start answering your questions. After we've gone through all of these demos today, are you now considering applying AI to any of these applications? That can be perception, motion planning, or control systems, or maybe something else. You can put that in the chat if you have some other ideas as well.
Or even if you are already working on one of these and using AI algorithms, that will be helpful to know as well.
And with that, we'll jump straight into questions. So put your questions in the chat, and we'll get them here, and we'll try to answer a couple. The question was, I showed up late, are we doing all of this artificial intelligence in MATLAB? And the answer is yes, we covered everything in MATLAB, but of course there are other tools out there.
And we also showed how you can integrate or interface with external tools that lets you build AI models as well and bring them over in MATLAB, or bring your MATLAB AI model, deploy it on external tools. So there is that interface exist as well.
Things like TensorFlow or Onyx-based transformations.
But yes, you can do everything in MATLAB, from building your model, labeling it, training it, and finally deploying on a real hardware.
Let's see if we have any more questions. Okay, labeling and learning is a time-consuming task. Even if it's automated, it can take time. How can it be optimized? That's a really good question. Here, would you like to get started on that?
Yeah, I can see the pain, but I haven't found a way to optimize it. Mostly I've used the automated labeler app, and it has done the job pretty good. But yeah, it will be great to find some ways to even optimize it further.
Yeah, so we covered some tools, and there will be links in the chat on how to do this sort of automatic labeling, which is really helpful. Sometimes, again, it's not perfect. It will make some mistakes, but when you're talking about thousands of labels or images to label, it's really useful. So then you can just kind of scroll through them really quickly and just spot the mistakes instead of having to label all of the objects in it. So I highly recommend you look at those. Let's see.
What kind of hardware do I need to do these demos? So that's a good question. We have a couple. We support a lot of different types of robot hardware. So the ones that we showed for robot arms, there were Kinova robot, and the other one is UR, Universal Robot. I think I forgot which model do we support. The UR5?
UR5, yeah, but I think in general we have support for ROS as well. So if you have a ROS-enabled robot and you're interested in adjusting any of the things we showed today, you could do that. But also, if you're thinking about just trying this on your own as soon as possible, there's simulation versions of these demos that you can just try in Gazebo or one of our simulators.
Yeah, and we can import a lot of different types of robots URDF, so you can actually see a real-world robot hardware like something like a UR robot within MATLAB with their specific actual parameters.
And if you're like a robot designer and you have your own robot, you can even import that into one of our simulators, and then you use that to implement AI or some of the things we showed today.
But quickly getting started, any low-cost robot hardware like we showed in the ChatGPT demo can also be used.
Okay.
Great questions.
Yeah, some good questions. I think we're pretty much at the top of the hour. Thank you everybody for attending. You're welcome to leave questions and comments in the chat. I think that's all we had for you today.
And we have a bunch of resources for you to look at, so we'll share that in the chat as well. Please take a look at these resources at your own time and feel free to reach out to us if you have any questions further.
Yeah. Thanks,
Right.
Mihir. Thanks everybody for
Thanks,
attending.
Jose. Thank you, everyone.
Okay, have a good one.
Yep.